Before we get into the Compton effect in this video, we're going to just go over the history of electromagnetic radiation and light. So remember, we started off where we had Newtonian physics and light is a particle. But then we had people such as Maxwell, Young, and Huygens who through experimentations and calculations showed that electromagnetic radiation or light is actually indeed a wave. This held true for a long time until the ultraviolet catastrophe occurred. This happened under Rayleigh and his black body radiation experiments, where they took things and they were testing metals, seeing how hot they get and stuff like that, and they were curious about it. And then they started graphing it, and there was a catastrophe. It did not fit the wave model or the calculations of what should happen if these are waves. And then Planck came around and he mathematically started quantizing our light. And he says, well, if you quantized light and quantized this energy, now this black body radiation curves work. Which he didn't think much of it at the time, but it ended up having a very significant impact in physics. After that, we ended up having someone like Einstein coming along, looking at the photoelectric effect, and he kind of went with this quantized light of Planck and looked at it through the photoelectric effect. Now, remember, we've had so many years and experiments that's shown that light or electromagnetic radiation is a wave. It can't be this photon that Einstein came up with until all of a sudden Compton comes along. And that is what this video is all about. How Compton took Newton's photons idea, which is technically a particle, which goes against all classical physics, and did an experiment to push and prove it. But to understand the Compton effect, we must first look back to things we've looked at before. Since we're dealing with particles, we have to understand the conservation of momentum and the conservation of energy. And since what Compton did essentially was shoot an X-ray at an electron, then both the X-ray photon and the electron must obey the law of conservation of momentum and the law of conservation of energy. And with his experiments, voila, proof, light is a particle too. So what is the Compton effect? Well, in 1923, an American experimental physicist named Arthur Holly Compton performed an experiment in which a beam of high X-rays shot at a thin piece of metal. Now if we look at this, this is very similar to the photoelectric effect, except instead of using light rays, we used X-rays, which we know have a shorter wavelength and a higher frequency. Now, he found something very different here. Yes, still an electron was liberated, but something else happened. He also noticed, like right here, that there was an X-ray of a lower frequency emitted as well. And we also know from before that energy is equal to Planck's constant multiplied by the frequency. So if I lowered the frequency of this photon here, what ended up happening was we had less energy. So Compton surmised then that this energy was being transferred to the electron. So indeed, we have a collision and a rebound, like golf balls. So once again, we're looking at light being a particle. And this proves light being a particle, or quantized, like little quantities of photon lights are actually holding these waves. And this idea led to what is now known today as the Compton effect, which basically states we have a photon of high frequency coming in and it hits this little electron here. The electron shoots off this way, but then we have a frequency or a photon with a low frequency leaving that way. Now we have energy here and energy here and energy here. So my initial energy must equal to my final energy. And also my initial momentum must equal to my final momentum. Because now we're looking at particles. To explain this phenomenon, what Compton did was he treated this collision as if it was a collision between two particles. And therefore, the conservation of energy and conservation of momentum laws would have to apply. But two main challenges came from this. First, we learned before through Maxwell's electromagnetic radiation theories that electromagnetic radiation is a wave, not a particle, and this contradicts that. Secondly, photons or light does not have a mass. So how can it have momentum? If the mass is zero, it cannot have momentum. Well, Compton was actually able to use Einstein's famous formula that many of you have heard, E is equal to mc squared. So energy is equal to mass times the speed of light squared. This is a very simplified version of the formula. And this allowed for some interesting calculations that prove Compton to be correct, which put more fuel in the fire, explaining that, well, maybe electromagnetic radiation and light are particles and not a wave. So first, let's look here at the momentum of this collision. So Compton had a problem. There's no mass. How could there be a conservation of momentum without a mass? Well, what he did was he took Einstein's equation here and he isolated for mass. So we have mass is equal to energy divided by the speed of light squared. So in other words here, we could plug this in for the mass. So we end up getting my momentum is equal to my energy divided by my speed of light squared multiplied by the velocity. So now both of these velocities here will end up canceling out, so I get E over the speed of light, which is c. But we also know that the speed of light from before is equal to my frequency multiplied by my wavelength. So I'm going to plug this here in for c, which is going to end up giving me my momentum is equal to E over the frequency times the wavelength. Now we also know that energy is equal to Planck's constant times my frequency. So we're going to do one more substitution here, and I'm going to end up getting Planck's constant multiplied by my frequency divided by the frequency divided by the wavelength is going to be my momentum. And now we cancel off these frequencies, so I end up lastly getting my momentum is equal to Planck's constant divided by my wavelength, which is the exact same formula that you have on your formula sheet. And there he was able to completely eliminate the mass from the energy of the photon coming in. So he was able to figure out the momentum of the photon without knowing the mass. Next, we're going to look at the conservation of energy. And remember, in this collision here, we're looking at an electron. An electron can't change its size, so we're going to have to assume a perfectly elastic collision. So we have our photon coming in here, and it hits this electron. Now the electron's going to go this way, and the photon scatters off this way. The only thing that really changes is the photon is going to have a different wavelength now. The wavelength is going to be bigger, and the frequency is going to be smaller. Now if we remember from before when we did particles colliding, my y's value must be the exact same on the collision. So in this case here, there's 0y, so my y values must be the same. So this y value must equal to this y value. Do we get that? And what else we know is this x value here plus the x value of the top must equal to the x value of my initial. Just same thing that we did when we did collisions in our very first unit. Now, this here is on the formula sheet. You could ask me if you want how to do that, and I can show you in class how to come up with this. But this is very key here. What this shows is the angle of the photon determines more what is going to be the difference of the wavelength. So my angle here determines the difference of the wavelength from here to here. If this is a large angle compared to a small angle, is the biggest factor in determining how much of a wavelength change I'm going to have. Because Planck's constant is a constant. The mass of an electron, or the mass, is constant. The speed of light is constant. So the only thing that's really changing here is my angle. And then eventually my wavelength. So those are my two changing variables. So another thing we have to look at here is momentum is equal to Planck's constant divided by lambda, whereas energy is equal to momentum times the speed of light. So I could just plug this in there. So in other words, we could say energy is equal to Planck's constant divided by the wavelength multiplied by the speed of light. All right, let's get to our first example. So my first question asks, what is the momentum of a photon that has a wavelength of 1.2 times 10 to the negative 12 meters? I'm going to look at this here. We know my wavelength is equal to 1.2 times 10 to the negative 12 meters. And we're trying to figure out what is my momentum. So here we know momentum is equal to Planck's constant divided by my wavelength, which is equal to 6.63 times 10 to the negative 34, and that's joules seconds. And that's all going to be divided by my wavelength, which is 1.2 times 10 to the negative 12 meters. Now I divide these here, and I'm going to end up getting 5.53 times 10 to the negative 22 kilograms meters per second. In my second example, it asks what is the frequency of electromagnetic radiations whose photons have a momentum of 2.8 times 10 to the negative 7 kilograms meters per second. So we know my momentum here is equal to 2.8 times 10 to the negative 27 kilograms meters per second. What are we trying to find here is we're trying to find my frequency. Now that's where this one's a little bit complicated. We're going to have to do quite a bit of substitution. So first of all, we know momentum is equal to Planck's constant divided by the wavelength. But we also know the speed of light is equal to my wavelength multiplied by frequency. So wavelength is equal to the speed of light divided by frequency. So I'm going to plug that in for my wavelength. So I get momentum is equal to my Planck's constant multiplied by the frequency divided by the speed of light. Now, we're still here looking at this. We have to isolate for my frequency. So my frequency, we are going to end up getting momentum multiplied by the speed of light divided by Planck's constant. So now let's plug in everything we know. We know momentum is 2.8 times 10 to the negative 27 kilograms meters per second. I know my speed of light is 3 times 10 to the 8 meters per second. And we're dividing that by Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds. Now when I plug this all in together, I'm going to end up getting something around the line of 1.3 times 10 to the 15 hertz. And that is going to be the frequency of this. So in our second last class example here, we have an X-ray photon with a wavelength of 0.05 nanometers, scatters at an angle of 30 degrees. Calculate the wavelength of the scattered photon. So this is what's given. We are given my wavelength and the angle. And these are the only two things that change in the formula as soon as we're looking at angles for the difference of wavelengths, how the wavelengths change, if you remember for what we talked about before. So we're going to be looking at this formula here, but my main problem is we have the change in wavelength. Well, the change in wavelength is my initial wavelength minus my final wavelength, which is this right here. So now we're really going to have to use this formula. And we're trying to find the final wavelength, so I'm going to take all of this and I'm going to add my initial wavelength, or my initial wavelength add all this to isolate for my final formula. Your book does this slightly differently. They first put this, they looked at this, and then they substituted in this formula here for your wavelength. But it's essentially the same thing. And then they put in all the variables that they know. All of these here, remember, Planck's constant, the mass of our electron, and the speed of light is all constant, so the only changing things are my initial wavelength and whatever the angle is, and that will help me determine my final wavelength. So once we plug all of these in, we end up getting this for an answer. So here is a problem for you guys to try and do yourself. The answer for this problem is this right here. Here's our last example of the day. This one here says, what is the maximum change in wavelength that 0.01 nanometers X-ray photon can undergo by Compton scattering with an electron? Does this wavelength of 0.01 nanometers matter in this example? We're looking at maximum change. Well, here's what's given. We know the wavelength, but does that matter? But first we're going to figure out what is the maximum change. So the maximum change will occur when the X-ray is scattered by the greatest possible amount. Well, let's look back at this formula here. The greatest possible amount is going to be when my angle is 180. Why is that? Well, if we remember back from Math 20-1 or even Math 30-1, what you end up learning is through your trig circle is that cosine relates to the x values. So if I have my quadrants here, cosine is going to relate to the x values. And we are subtracting cosine. So this is positive 1. This, on this side here, will be negative 1. So 180 is going to give me negative 1. So it's going to be 1 minus negative 1, based on our trig identities from before. So 180 is going to be the maximum degree of which we want to use. And that's going to end up giving us a solution of somewhat like this. So really, we do not need this initial wavelength at all, because we're looking at the difference of them. What is the difference? So we just need to know delta wavelength. And no matter what, when I go 180, that's going to be, well, minus 1. 1 minus 1 is 2, so it's 2 times Planck's constant divided by the mass of the electron multiplied by the speed of light. So altogether, we're just doubling whatever this constant area here is, and that is going to be my maximum change in wavelength. And that's pretty much the maximum change of wavelength we could have in all. It doesn't matter anything else. So here are three more practice examples for you to try. I lied, we do have one more video here to do, and that is, what is the momentum of a 6 megavolt or mega electron volt proton? So we know my energy for this one is equal to 6 times 10 to the 6 electron volts. So if we're looking at this here, we're trying to figure out momentum is equal to my question mark. So I'm going to use the formula energy is equal to momentum times the speed of light. So we're going to rearrange this so momentum is equal to energy divided by the speed of light. Now my energy has to be in joules, so I'm going to go 6 times 10 to the 6 electron volts, and we're going to multiply that by 1.6 times 10 to the negative 19, and that's going to be joules per electron volts. And this is all going to be divided by 3 times 10 to the 8 meters per second. When I plug this in, I'm going to end up getting 3.2 times 10 to the negative 21 kilograms meters per second as my momentum.